Okay, in this video I'm going to talk about volumes of revolution. What we're going to do is we're going to start with a curve. Alright, so I have a curve right here, y equals f of x, that follows this path here. And I'm bounding that curve between a and b. Now at this point we can look at the area under the curve. Alright, then what I'm going to do is I'm going to take this whole region, this whole area, and I'm going to revolve it around the x-axis. And when I do that, what I end up with is this three-dimensional shape, alright, this whole three-dimensional region that I can now take the volume of. Alright, so that's going to be our basic idea here. So I've got these two shapes. Now, let's look at the area under the curve. We figured out that we can represent the area under the curve by taking these slices, right? And the width of each slice, the width of each slice is delta x, and the height of each slice is the value of the function at x. Alright, so you have a point x and you take the height of the function there. And if we do add up all of these intervals, alright, all of these slices in here, we get something that approximates the area. And if we let the number of slices go to infinity while delta x goes to 0, alright, what we end up with is the definite integral. That is our definition of the definite integral. And it represents the area under the curve. Alright, so what I'd like to do is I'd like to take this concept and extend it over here to our revolved area. Alright, so we take this area, we revolve it around the x-axis, and we get this three-dimensional solid. Alright, now just like I took a slice over here with the function to get the area, alright, so let's call that A for area. Alright, just like I took a slice over here, I can take a slice over here, but a slice over here is a rectangle. A slice over here has to be a disk, right? Because it has to basically take a nice disk shape out of our solid here. Alright, we still have the same delta x for the width. Okay, so we'll leave that. Now, let me come out over here for just a second, and let's look at a disk. Alright, so if I just take a rectangular disk, alright, without worrying about the function, and I want to figure out the volume of this disk, I have to consider the radius of the front-facing circle, or the radius of the disk, and I have to consider what would be the height of the disk. And when I do that, we have a formula from geometry, right? It's pi times the radius squared times the height, and that is the volume of the disk. Alright, so if I come back over here and I look at the disk that's actually in my revolved solid, alright, the radius, what is the radius going to be? Well, the radius is sitting here on the original function. Alright, so my radius becomes the function. And the width of my disk is delta x, and in the integral form that's dx. I have to multiply that by pi, and then I need to take care of the length of this revolved solid, which is going from A to B. And so from A to B. Alright, so that's my basic formula for the volume of a solid that's obtained by rotating the area under a curve around the x-axis. Now there's one other thing we can do with this, right? Because when we're doing areas under the curve, we always have the possibility that we're looking for the area between curves. So if we have, let me just put two arbitrary curves up here. So suppose we have two arbitrary curves here. We'll have f of x g of x. And suppose again I'm looking for the area between two bounds here, a and b. Alright. So I'm looking for this area in between these two curves. Now the area between the two curves, remember how we do this, right? A to b. Take the top curve f of x, and we subtract the bottom curve g of x dx, and that is the area between the curves. Alright, the only difference that I need to worry about here when I take this and I rotate it like this around the x-axis and I create this solid form is, I'm not going to try and draw that in 3D, okay, is the two different radii. Alright, so I have one radius that's starting up here going down to the x-axis. Then I have a second one that's starting there and going down to the x-axis. And just like here, take the larger one minus the smaller one. So in this case, I'm looking at volumes. So I have to take the larger volume minus the smaller volume. Alright, so I'm going to do a to b pi. The larger volume is given by f of x squared dx minus pi times the smaller volume, which is g of x squared dx. Okay, and actually I should throw a... I'll write it this way for now. Alright, so we can simplify that a little bit. We can always pull the pi outside because it's a constant. We can make this all one integral. And then we're just doing f of x squared minus g of x squared dx. Alright, now the difference between the two, the difference between looking at a solid like I have here and a not solid, wait, where did I, oh, I see what I did. Alright, and a region like this, in terms of material science, is, think of a container. Alright, I'm either looking at the volume of a container, or I'm looking at the materials needed to make the container. Alright, that's the easiest way to distinguish between the two. Alright, so if you're looking at materials engineering, alright, something like this, you would be looking at the wall thickness. Alright, this would be representing the thickness of the wall of the container. Whereas this one is representing the volume of the container. Right, and that's the those are the two examples that we're going to look at. Alright, so let's suppose you need to put together a container. And you're interested in the volume of the thickness of the walls because you need to figure out the amount of material you're going to need to make the walls of the container. And after some research you've done, the shape of the container is very particular. Alright, it has to follow... the heck? Oh, I see what I did. Alright, it has to follow, for the outer wall, e to the x, and for the inner wall, x squared plus 1/2. Alright, so if we look at this, and you can graph this on your calculators, alright, if you look at this, alright, we want this container to be, alright, so we have a container, it's going to be 1 meter tall. Alright, so we're going to use our x-axis to represent the height. So we're going to go from 0 to 1. Let's put 1 out here so we got some room to maneuver. Alright, then if I graph these two, y equals e to the x, that's going to cross here at 1. I'll put 1 down here. And that's going to go up like that. and then y equals x squared plus 1/2 is going to cross here at 1/2. And it's going to go up, but it's going to go up at a slightly different rate. Okay, it's going to go up a little bit slower, and then it's going to jump up like that. All right, so what we've got here is the container's side in 2 dimensions. All right, so what we're going to have is we're going to have a container that sits more or less like this. And we want the base walls to be thicker at the bottom than they are at the top. I'm exaggerating this, okay? Alright, so we want the base walls to be thicker at the bottom than they are at the top. Alright, so we take this and we rotate it around the x-axis. Alright, to find the volume of the walls, we're doing the antiderivative from 0 to 1. And then the curve on top is e to the x. So that's going to be, let's throw a pi outside. Alright, e to the x squared minus the bottom curve is the parabola. So that's going to be x squared plus 1/2. Alright, and all that is dx. Alright, so there's your setup. And I forgot to square that. There's your setup. Alright, now this one's not hard to do by hand. Alright, we could certainly go through and do all the mechanics by hand. But the trick with a lot of these is you're going to end up with certain combinations of functions that you can't anti-differentiate. So because of that, my suggestion is going to be use your TI-89s, alright, or your TI-83s, either one of which will work to do a definite integral. Alright, so what we're going to do is we're going to go input on TI calculator. Alright, and there's a video up how to do that already on both the 89 and the 83. Alright, and when you put this onto your TI 89 or 83 calculator, it's going to spit out approximately 7.575. Okay. Alright, so what this tells me, because I started with meters, alright, this says that I have 7.575. We're going to volume, so that is now meters cubed of material. Okay. Alright, so there's an example of what you might use this for. Alright, now I have one more example, alright, that involves calculating the volume of a tank. Alright, so we have a fuel tank. Alright, I'm spelling fuel wrong, aren't I? A fuel tank. Alright, and the fuel tanks outside follows this function, f of x equals, and this is a composite function, and we'll see why in a minute, 4 times the square root of 10 when x is between -120 and 10, and 1/5 square root of x times 30 minus x when x is between 10 and 30. Alright, so here's what we're looking at. Here's the shape of this fuel tank. Alright, so the two curves we're looking at from -120 all the way to 30. Alright, I did it again, -120 to 30. this is just going to be a straight line, right? This is just going to be a line that intersects the y-axis at 4 rad 10. And it's going to go all the way up to 10, so that goes to there. And then from 10 to 30, we've got basically this downward facing parabola that intersects at 30. So from there, we're going down like that. All right, so if we take this and we revolve this around the x-axis, I end up with basically something that looks like a rocket or a fuel tank, or however you want to think of it. Okay? All right. So I want to estimate, the whole point here is I want to estimate the volume of hydrogen, liquid hydrogen fuel, that will fill this tank. Alright, we're ignoring some basic things like the thickness of the tank walls. Alright, compared to the volume, the thickness of the tank walls are almost negligible. Alright, and we're really just looking for an estimate. Alright, so if we want to estimate the volume that's going to go in here, alright, so I actually have two functions and I have a place where they split. So from negative 120 up to 10, alright, we're looking at a constant function. It's 4 square root of 10 dx squared. Alright, then we have to add to that the second half, which goes from 10 to 30. Alright, and that's going to be 1/5 square root of x 30 minus x squared dx. Alright, now again, best bet here, you can work this out by hand if you want, but I would just input this into the calculator. You might want to do a little bit of work to clean it up before you do. Alright, like we could take this first part here. Alright, if I square this, I get 160. Alright, so I would put 160 pi in. Alright, and if I square this out, I have 1 over 25, so this is going to be pi over 25. And then x, and then 30 minus x squared. Alright, so all of this replaces what's in there when you work it out. And then this, you're going to put in the calculator on these bounds. This you're going to put on the calculator in these bounds. Okay. Now when I put this into the calculator, this first part comes out to be 65,345. Actually 0.1 according to my calculator, so I'll put that there. Plus, and then this part, when you put it into the calculator, comes out to be 5,026.55. Right, so we get, what do we get here for the total? 371.7-ish. Okay, which is roughly, now again, all this is measured in feet. Alright, so this is all measured in feet. Alright, so we get approximately 70,372 square feet. Feet cubed. Alright, so we're going to need 70,372 cubic feet of liquid hydrogen. Alright, if you want to change that to a more manageable unit, pick your favorite unit converter, alright, and convert that over to gallons. The TI-89s will do it, though mine seems to be having a problem doing it, so we'll have to try that out in class maybe on Monday. But if you convert this over to gallons using a unit converter, you end up with 526,419 gallons. All right, so that would be the volume of the fuel tank. All right, so if you missed class today, that was basically what I went over. All right, I did assign homework, so you can take a look at the homework. Is on page 528. And I said numbers 1 to 33. Remember, the odd answers are in the back, so if you want to do the odd ones, that's fine. Okay? And I will see you all on Monday.